All right, let's get started. You're gonna like today because it's not. Even the homework is pretty nice to you. We're starting with vibration Raman spectra of diatomic molecules. So before we talked about infrared spectroscopy, and you had to have a changing what for it to be IR active, Pablo? For this molecule to absorb infrared radiation, had to have a changing dipole moment. Yeah, dipole. What change dipole? Same thing, right? Okay, now for it to be Raman active, needs to have a changing. What was the key thing for Raman? Right.
It was the scatter was the same wavelength, or you lost energy.
Yeah, you can lose energy or gain energy.
Yeah.
And that's Raman. You have ray. Yeah, well, back up. That's not. We're kind of getting off target a little bit, but just to cover what you're talking about, that's what Raman spectroscopy is. Interaction, all spectroscopy, interaction between light and matter. Light can be scattered. If you have two different ways, one way where you can gain or lose energy, that means you're going to be red shifted or blue shifted. The scattered radiation will be. The other way to scatter light is like our sky. It's an inelastic collision. The wavelength doesn't change. That's Rayleigh. So there's really no interaction between light and matter. That's really not spectroscopy. So we want to talk about where there's an actual exchange of energy. So that's Raman spectroscopy. For Raman spectroscopy to occur, what has to happen, or what property does that molecule have to have?
Anisotropic polarizability.
There it is. All right, say it one more time.
Anisotropic polarizability.
Anisotropic polarizability. Excellent. So that's essentially what has to happen for a molecule to be Raman active. That vibration has to have a changing polarizability, right? While it's vibrating. Okay. So likewise, with IR spectroscopy, we had these branches. Here they just call them the O branch and the S branch, depending on your J quantum number, right? Whether it's delta J2 or -2. And then you get your branches, just like they're just trying to exhibit that it's kind of similar to IR spectroscopy, right? I think this is kind of interesting, this idea of normal modes, because I don't know what you imagine when you imagine a molecule interacting with light, right? I mean, we have, let's see, this kind of thing can happen, right? But in my mind, it's much more jumbled than that. I mean, you've got rotations going on. You've got all these vibrations going on at the same time, right? This is just water. So it's going to be, this is a very simplified picture, I think, of what's going on. It's just going to, I think of each one of these different modes as a standing wave, and you just simply add that action, and then you get the total motion of the molecule. Then you got to throw in translation too, flying through space. So there's a lot of different modes of motion. And that's where they're coming with this word, normal modes. And that you can excite just one of these vibrations without interacting with any of the other vibrations or any other type of motion. So it's kind of like those irreducible representations that you can keep reducing things down to a certain point, but then you can't reduce them anymore. So with vibrational motion, you just can't reduce things down any more than the normal modes. So typically, when you think of vibrations, we just never used the word normal modes before. That's what we've been talking about this whole time, is normal modes. Okay, and you can have like symmetric stretch. They kind of labeled it for you, but symmetric stretch, right? They have to be, the vibration has to be occurring symmetrically about the center, right? See the difference with an asymmetric stretch with water? It's not symmetric motion. Would both of those, Ricky, be IR active?
Which one?
Or do you see any IR inactive? Let's put it this way. Do you see any IR inactive vibrations? Now, that one in the upper left, that's not a vibration. There's only 3.
Because wouldn't, even though the upper right one is a symmetric stretch, wouldn't it still be IR active because of the oxygen being so electronegative? Or no?
Yeah. Is water polar?
Yes.
Water's polar. So the only way for you to remove any vibration of water from being IR active is to remove that polarity somehow. I don't see how the heck you're going to do that if a molecule's polar in the first place, right? So then they're all going to be IR active. And some are just worse than others, I guess, right? Does that make sense? Because the water's just permanently polar. You can't do much about it. Is this where I wanted to mention the equation? No, I don't want to mention. Well, I guess I can, right? These numbers of normal modes. Can I write on here? Will it let me? No, I lost it. So if you have a linear molecule versus a non-linear molecule, right? It's kind of a nice thing to remember. It all comes down to degree of freedom. And I don't know how well you remember analytical chemistry, where we first introduced degrees of freedom. But essentially, it's the idea in my mind for degrees of freedom it comes down to mathematical equations. Because we all have the understanding, if you have 5 variables, how many equations do you need to solve it? 4, right? Makes sense. So think of motion. You've got rotation, translation, vibration, right? You have all these different modes of vibration. Well, you have mathematical equations that are going to represent them all, right? So why not, once you figure out you're going to have a set of equations, that means it's the same type of thinking. You only need so many, define so many equations, and you can solve for the last ones. So there's a limit, is what I'm trying to say. There's a limit to these things, to rotations, vibrations, translations, and there's a limit to the equations that you need to solve all this stuff. Very different than analytical chemistry. Analytical chemistry was talking about statistics and uncertainty. So how many equations are needed to discern the statistics of this system? Well, you have average, you have standard deviation, right? You have all these statistics. And once you use one up, the others are defined. So again, you have degrees of freedom, depending on the number of measurements and all this. Okay, this is narrowing things down solely to vibrations in normal modes. And these relations give you the number of normal modes. So n is just the number of atoms in that molecule. So is water linear or is water bent? Water's bent. So it would qualify under the nonlinear category. So water should have, how many atoms does water have? 3. So n would be 3. 3 times 3 is 9. Minus 6 would be 3. So water should have 3 normal modes of vibration. Did they do the diagram right? I think they did. Yeah, they drew 3 of them. That's all they can draw. It's just 3. Okay. All right, so I think we covered that. Okay, how about CO2? Let's take a look at CO2. CO2, how many normal modes of vibration should carbon dioxide have?
Carbon dioxide?
Yeah, carbon dioxide.
Oh, it's a linear, so it would be
Carbon dioxide.
Yeah.
1. 1 has 3 molecules. So 3 times 3 is 9. Oh, minus 5. Sorry. Not bad.
Carbon dioxide.
Are they going to show another one?
No. Well, we said linear was 3 minus. Yeah, we're missing one. Well, that sucks.
Yeah, you should have 4.
Now we're missing one. I'll have to Google that one.
Yeah, maybe it's missing one.
Okay.
Maybe it only shows like the top 3.
Ah, we're missing one. Okay, anyway. What one could we physically be missing?
Oh, that's a good question.
Huh, I'll say Google that one.
Is spinning never a mode of?
We're talking about vibration, not rotation. So it's kind of interesting in the sense that each one of these normal modes has its own ladder, right? This is the symmetric Morse potential. Completely harmonic is the word. But can this bond ever break? No. We need some anharmonicity, right? So each one of these normal modes has its own vibrational ladder. As you go up the ladder, what changes? Yeah. Does the frequency change? Each one of these normal modes.
No.
Think of the spring. Think of the spring. And I pull it down.
So
The amplitude changes. So the amplitude just keeps increasing, getting more and more violent as you go up the vibrational energy ladder, right? Until it finally will break. That's only if it's anharmonic, right? It starts getting anharmonic. Okay, so it's not harmonic anymore.
So it's E equals HC over.
So what I'm getting at here is that each normal mode has its own set of vibrational ladders. Now you mentioned rotation. Each vibration, now you have to pop this guy open and take a look at him and really zoom up, then he's got his own rotational ladder. So each one of these is a vibrational, right? Each vibrational mode has a Morse potential that looks like that. That's kind of what you're asking, but okay. How about this one? Would there be any IR inactive vibrations? Do you see any IR inactive vibrations? No?
Isn't, I keep thinking the upper right hand.
Yeah, the upper right one would be inactive.
Yeah. You should be able to see that upper right one is IR inactive. Every instant in time, those dipole moments are canceling out,
Okay.
right? Can you picture it?
Yeah.
Even though there's be 4 up there.
Yeah, we're missing one.
I can't think of what the other one.
I don't know what it'd be either. I gotta Google that. I gotta Google that and find out. Okay. So anti-symmetric stretch, symmetric stretch, normal modes. Okay. Oh, I should have left the CO2 one up. So now they want you to, these bands and parallel and perpendicular bands. Again, what is a band? Here's a band, right? So they name them parallel bands and perpendicular bands. What's going on there? Let's go back to CO2. So if the vibration, where's the principal axis? Where's the principal axis of rotation in this? How would you draw it?
The x-axis.
Yeah, right through the entire molecule, right? Yeah, if you want to call it the x-axis, or right, it goes right straight through here. So is the vibration parallel to the principal axis? Is the vibration here parallel or perpendicular to the principal axis? Parallel. So this would be a what band? A parallel band. Here the vibration is perpendicular to the principal axis. So this would generate a perpendicular band. That's all they're after. Just depends on the principal axis. Force field, I think all you kind of picture here is a three-dimensional surface or space, and this is completely imaginary. And this has these imaginary dots, and each dot represents a K, a spring constant. So the closer you, so depending on where you're at, you can get different spring constants, right? So it's either harder to move or it's easier to move, depending on what that spring constant is. So it's just an imaginary space with points in it with different spring constants, some higher, some lower. Okay, tumbling is random motion of a molecule in space. This idea you're going to need to get through some homework questions. They call it the exclusion principle. And when the homework's asking you, is a particular vibration Raman active or IR active, especially when they mention the word Raman, keep this in mind, because pretty much all molecules are Raman active. I mean, my goodness, everything's changing polarizability. I mean, that's pretty hard to not to have. Okay, so this is pretty much the only way that I can guarantee you can knock it out. A normal mode of a molecule, so they're talking about a vibration, normal mode of vibration with a center of symmetry cannot be both infrared and Raman active. So once you figure out, if you have a molecule that has a center of symmetry, what has a center of symmetry? Does carbon dioxide have a center of symmetry? Yeah, right? Carbon dioxide has a center of symmetry. So if you have a, well, we go, there it is. You have a vibration that's like this one up here. Is this vibration IR active? No. So it could be Raman active.
Does that mean it necessarily is or no? No, it doesn't mean that.
I don't think it necessarily is. What they're saying is it can't be both. It can't be both. So a better one would be picking one like this one. Is this one IR active? Yes. So can it be Raman active? No. So you can't. That's how they play that game. They call it the exclusion principle. Depolarization ratio. All they're pretty much what I wish they would have kept going on here. You see this black line? That's their, I should have drawn this in black. That's their incident radiation. Okay, and they're just trying to talk about whether the light is polarized or unpolarized. And if that ratio is greater than 0.75, they call that depolarized. If it's less than 0.75, they call it polarized. So I don't think this is even in the homework. So I don't know, maybe where they're coming from is if you want to get this polarized scattered light, right? If you want to get this polarized scattered light, you have to have a totally symmetric vibration. And I don't know, I think this is more information than you need. If you want to get polarized scattered light, okay, you need a totally symmetric vibration. I guess another idea you can get out of this is if you're going to set up a Raman instrument, you'd always detect your scattered radiation 90 degrees from the incident, right? In that sense, it's kind of like a fluorimeter. It's set up that way. And then now they're digging a little bit into Raman spectroscopy, and you can really enhance Raman spectroscopy, make it much more sensitive. If instead of picking any wavelength to scatter, pick a wavelength that it actually absorbs at. So take an absorbance. You know what the absorbance spectrum is of this compound, and the peak is at 545 nanometers. Well, let's do Raman spectroscopy with that incident radiation at 545 nanometers, and then the scattered radiation is much more intense. They call it resonance Raman spectroscopy. And again, now cars, you don't hear about this stuff too much anymore, but you see two frequencies here. So that's just two lasers. So instead of using one laser for scattered radiation to do Raman spectroscopy, they use 2 lasers. And we'll just kind of leave it at that because I don't want to, it's not really going anywhere. Okay, so now we're here. Let's take a look at some of these. Okay. In 12, we have a molecule that belongs to the point group C2V. And the displacements of the atoms. I guess that's, there's shortcomings of every book, but you pretty much have to, I wish they would put more words in their questions. They might be longer that way, but it would be better. What are the possible displacements of a molecule, of an atom in a molecule? What can it do? I mean, for example, we know it can vibrate. So that's one mode of displacement. It can rotate. So there's another set of displacements. And there's only one left. We've got vibration, we've got rotation. Translation. Right? Translation. Wake up, Ashley. So those are the 3. So the idea here is, okay, here's all of the irreducible representations for all the displacements. All we want to know is what are the symmetries of the normal modes of vibration. So we need to subtract out the rotations, subtract out the translations, and we'll be left with the vibrational modes of displacement. Okay. The trick to doing this is pretty much looking at what character table? C2V. Okay. And then we find, might be easier just to have one. Let's see. And then you'll see it. Yeah. Do you have one of those in that book? Oh, we do. On page is like 54, it looks like. C2V?
Yep.
Okay, that's on page 54 in the book. Okay, so now look for, let's subtract out the rotations first. Hey, okay, let's subtract out the rotations first. Now, if you're looking at the C2V character table, what would you guess is representing the rotations? Right, like look over here. What functions? Probably the big what?
R?
The big R's, right? And you've got an Rx,
Yep.
an RY, and an RZ. Okay, so the Rx spans what? Let's subtract out the rotations. The Rx is what? Which irrep? A, B, C, or no, there's no C.
B2.
B2. Okay. Subtract out all the R's. What's the R? RY is
B1.
B1.
And RZ is A2.
RZ is A2.
Yes.
Okay. I guess we could say plus, right? Let's subtract out all those guys. Those are all of our rotations. Now we have to subtract out our translations. In our translations, looking at the C2V character table on page 54, what functions would probably say, hey, these are translations?
Words? No.
Translation. If I'm going to throw something across the room, how would you describe its trajectory? X, Y, and Z. Okay, so X is?
B1.
B1.
Y is B2.
Y is B2.
And Z is A1.
And Z is A1. All right, so let's subtract all these guys out. We got to subtract out 2 B2s. So that means we'd be left with 2 B2s, right? Are you with me? Subtract out 2b2s, subtract out 2b1s, so we're left with 2b1s. And subtract out an a1. I guess we forgot our a there, didn't we? Our little 1. Subtract out an a1, so we're left with 4 a1s. What else do I have to subtract out?
A2.
Thanks. An a2.
Why would it be 4 A1?
Because it was subtracted 1 from.
Subtract 1 from 5. Forgot the little 1 on the a, right? Because there is no a. It has to be a1. It's a typo. So, and then how many a2s?
You have 1.
You should have one of them left. Okay, now is this right? How many normal modes is this? 1 plus 4 is 5, 7, 9. That's 9. It's 9 vibrational modes. We have our molecule CH2Cl2. Is that linear or nonlinear? Definitely nonlinear, right? So that means we should have 3n minus
5.
3n minus 5.
I mean, nonlinear 6. Sorry.
Oh, it's nonlinear 6. 3n minus 6. Sorry.
That's right.
Okay. So n is going to be how many? 5. So 5 times 3 is 15 minus 6, 9. So we should have 9. Yep. So there's our answer. Those are the symmetries of the normal modes of vibration. You comfortable with that?
Yeah.
How many normal modes of vibration are there for the following molecules? Does anything look linear to you?
It's H2O. I mean, that's not linear, sorry.
Nothing's going to, right? There's no way none of any of that stuff's linear. So I mean, they all have 3n minus 3n minus
What
6.
about the C2H4 though?
It's symmetrical, but it's not linear.
Yeah, right?
It's not linear?
It's flat. It's planar.
Oh, I see.
Yeah.
It's planar, but it's not linear, right?
Gotcha.
I guess if you did
No, it's
this,
not, yeah. No, you're right.
Question 3. Sure you got it?
that would be linear. That should have been, they should have thrown in something like that, right? Otherwise, everything's nonlinear.
Huh. Hey, that's how you get things right. You gotta get them wrong 4 times.
So you're okay with 25?
Yep.
I'm sorry, I have a quick question on number 12. 4A1.
See the equation is a circle. There's 5A1s.
5A1s minus 1A1 is 4A1.
Oh, okay.
Huh? Oh.
And that 25 is just using the 3n minus 6, right?
Mm-hmm.
So it would be like for the first one, H2O plus 3n minus
Yeah.
3 times 3 plus 6.
Mm-hmm. Mm-mm.
Mine's first thing is for everyone?
No.
It's on
What?
that
You're
max.
buying us more pizza?
No. No pizza.
I don't
Ashley,
think I want to see
I
pizza.
can't pay for your pizza habit.
So you ready?
Yeah.
Which of the 3 vibrations of an AB2 molecule are infrared or Raman active? Now, what are they coming up with 3 vibrations of an AB2 molecule?
There's 3 atoms.
Yeah, 'cause there's only 3 atoms, so there's going to have to be 3, right? Okay. Are infrared or Raman active when it is angular or linear?
So that's where we do like our CO2 model and our H2O model. We know
Yeah.
H2O would be angular.
You're pretty much going to have to draw the dang
Like
thing
CO2
out,
and
though.
H2O.
Oh, it's 2 B's and then 1 A. I would have to draw them out. Otherwise, how else would you explain this? Right? So you'd have the symmetric stretch.
No, you had to write the reverse on those one.
What's that?
Oh, oops.
That's two B's and one A. You drew
I
two
did it
A's.
again. You know what I mean.
Oh well.
Right? And then you have the anti-symmetric stretch. Right? Then we've got the one where that little B's going up and down. Right? And then pretty much do the same thing for when it's linear.
Yeah, it's like trying to fly.
So draw symmetric. Anti-symmetric, and then this guy going up and down. Okay, so those seems to me those are your part A and part B. I don't know how else to illustrate the answers, right? You pretty much have to sketch these out. So when it's bent, just put a I next to it if it's IR active. Put an R next to it if it's Raman active. So, for example, this first one is both infrared and Raman, so just put it I, comma R or something. So then we'll all know what we mean.
We're not using the exclusion rule on this.
Does the exclusion rule apply to this? For when it's bent? Does the exclusion rule apply? Has to have a what? Center of symmetry. Does this have a center of symmetry?
Oh, wait, yeah, it does.
Yeah.
What is it? What is center of symmetry?
It's like a mirror plane.
A center of symmetry is a point.
Yeah, 1 point. So if
One
it's a vertical
point.
then
It's an inversion point. Where you reflect through there, you get the same thing all the time. This definitely does not have a center of inversion. Does the linear one have a center of inversion? Yes. So in which case, A or B, does the exclusion rule apply? B. Now you got to be worried about B. But A, right? So for the second vibration, so just, well, you do it. Do IR next to all of these and see if you agree at the end here. And remember, the exclusion rule is only going to apply for when it's linear there.
What is that A for? Like above the.
That's just part A, angular,
Oh.
and then part B is
Oh, okay.
linear.
I don't understand what IR active, Raman active. I don't understand why it does that.
What's IR active? How do you know something's a vibration is IR active? So you have to imagine this guy vibrating, right? A's going back and forth at the same time. Does it have a dipole moment? And is it oscillating in strength? It doesn't? How could it not? Think of how do you generate a polar molecule?
But like when it has dipole, like how do you know if it's how can you show it like that one is dipole, but is it because both A's are going down and like it's insinuating?
Is there anything to cancel out the electronegativity of these two? Forget about the vibration. This thing has a permanent dipole moment, right? There's nothing to cancel out the dipole moment of these two A's. They're down. Whether they're going, well, no matter what they're doing, you can't cancel out their dipole moment. The only way you can something like this. So now, but they need to move symmetrically. If they move symmetrically, they're going to completely cancel out their dipole moments. So as long as the motion is symmetric, it'll cancel it out. But here it's not. So this is going to have an oscillating dipole moment. So this one will be what active? IR active. Will it be Raman active? No, because of the exclusion rule. So this is only I.
So is it easy? Oh wait, only that one that is right under the B is not IR active, right? The rest of them are.
So this one is. We said, oh, what am I doing here?
Yeah,
Did I draw it under the wrong one?
Except that one.
I drew it in the wrong one, right? This one is IR active. I put up the I next to the wrong one. This one is IR active. We're talking about how it's anti-symmetric. It's IR active. So do you put an R next to it?
No.
No. The one up on top, is this IR active?
No.
No. Is it Raman active?
How can you tell?
Because IR, that one's constantly to the out.
No, I was saying how can you tell if it's Raman active?
It has to have a changing polarizability. So is the polarizability different whether it's out like this or like that? It's pretty much how it seems how things work is things are almost everything is Raman active. Pretty much everything is Raman active. The only way you can rule it out is the exclusion rule. And then your guess is right 99.9%, probably 99.99% of the time. Everything's Raman active. Because polarizability, come on, everything's polarizable. So the only way to really rule it out, in my mind, from what I've seen, is this exclusion rule. And say, oh, okay, well, this is the center of symmetry, so it can't be Raman active because it's IR active. Now, why is that? To conceptually look at that thing and recognize this does not have any anisotropic polarized. Come on, that's beyond my brain.
Yeah, you have to be a robot, like Pablo.
Yeah.
So then the one up top, on top of that one, is that one also I only? Because IR?
No, that one's Raman.
Oh, okay, the top one is just R because it cancel out.
Mm-hmm.
Okay.
You didn't get something to eat, Pablo?
All right.
You did?
So what letter? Let's make sure we all agree here. For this one, what letters did you put, or letter? I and R. I and R. This one, just R. Just I. Just.
I. No, just I.
Does it have an oscillating dipole moment?
Yeah. It's flying.
B's going up and down. So imagine B down here. Now the dipole is going up there towards A, right? Down here, now it's dipole's going down. So this definitely has an oscillating dipole moment. So just I.
Yeah, just like to find the fourth mode of vibration for the CO2.
There's, I'll have to Google that. I think there's a reason. There's a reason for that.